question from the past paper to help us understand Simplex method. And these are sample questions that I've picked from the quantitative analysis paper. This is December 2023. So in the question, we are told that a manufacturer of dress makes two types of dresses. And we have the standard and the executive dress. Each standard dress requires 10 labor hours from the cutting department and 30 labor hours from the sewing department. Each executive dress requires 20 labor hours from the cutting department and 40 labor hours from the sewing department. The maximum labor hours available in the cutting department and the sewing department are 320 and 540 respectively. The company makes a profit of 500 shillings on each standard dress and 800 on each executive dress. So required, formulate a mathematical model for the above linear programming problem. And part 2, use Simplex method. Determine the number of standard and executive dresses that should be produced in order to maximize profit. So every time you're given a question on linear programming, you have to determine what is the objective. And once you've determined the objective, it can either be a maximization objective or a minimization objective. The company can either be maximizing profit or contribution or minimizing cost. In this question, it is very clear that we are told it's a maximization problem, but sometimes you are not told, so you have to determine yourself. If you are given the unit profit or the unit contribution, then definitely it becomes a maximization problem. If you are given the unit cost of every decision variable, then automatically it becomes a minimization problem. And sometimes the question may give you both the selling price and the cost, so that the difference between the selling price and the cost gives you the profit. So in such a case, if you're given both the selling price and the cost, you have to subtract and get the profit, and you'll still treat it as a maximization problem. So in this question, because we are given the profit for each unit of the standard dress and each unit of the executive dress, we consider these as a maximization problem. Alternatively, the question has still said that under Roman 2, we determine the number of standard and executive dresses that must be produced in order to maximize profit. So just by saying in order to maximize profit, that is still another indicator that there is actually a maximization problem. So we know the problem of this company. The company wants to know how many units or how many dresses of the standard dress and how many units of the executive dress do they need to produce and sell so as to maximize profit. So the first thing that we have to do is we give our decision variables, we'll assign them algebraic designation or algebraic values. And I'll do that by saying we'll assign our decision variables algebraic designation and say that let the number of standard dresses to be manufactured and sold be X. Let the number of standard dresses to be manufactured and sold be X units. And let the number of executive dresses to be manufactured and sold. Be Y units. So now that we've assigned our decision variables algebraic designation, now we need to formulate the linear programming model. And because we've already established that it is a maximization problem, we'll start by developing the objective function and say that the objective function will be given by the maximum profit Z should be equal to what is the unit profit on 1 unit of the standard dress. We are told that a profit on the standard dress, 500 shillings each on the standard dress and 800 on the executive dress. And because our standard dress is X and our executive dress is Y, so we'll say that this is 500 X plus 800 Y, subject to, when I write ST, I imply subject to some constraints. So the limited resources available as per this question, we are told that the company only has available. Whatever is available is what represents the constraint, which means we cannot exceed this capacity. So the maximum labor hours available. So if you're told the maximum labor hours available, this actually represents a constraint. The maximum labor hours available in the cutting department and in the sewing department is 320 and 540 respectively, which means that we cannot exceed the capacity of less than or equal to 320 hours. And this 320 hours is labor hours in the cutting department. This is cutting department labor hours. And this is the maximum. Then you also have the second constraint, which cannot exceed 540 hours. And this is sewing department labor hours. Sewing department labor hours. So if this is sewing department labor hours and cutting department, so we need to know for every unit of the two products, to produce 1 unit of the standard dress, how many hours are needed? Each executive dress, each standard dress requires 10 labor hours from the cutting department and 30 labor hours from the sewing department. And that is represented by our X. So that will imply that that will be 10X from the cutting department and 30X from the sewing department, plus for the executive dress, we are told that each executive dress requires 20 labor hours from the cutting department and 40 labor hours from the sewing department. So 20 from cutting and 40 from sewing. So that this is plus 20Y and this is also plus 40Y. So that our constraint will be 10X plus 20Y should be less than or equal to 320 hours, and 30X plus 40Y should be less than or equal to 540. Remember, this question only had 2 constraints. That is why we only have these 2. But you can have as many constraints as per your question. So once you've written all the constraints, then we can also introduce what is known as the non-negativity and show that our x, y values should be greater than or equal to 0 to represent the non-negativity. So this implies that if the company cannot manufacture any standard dress, then the minimum they can manufacture is 0. The same case applies if they cannot manufacture any executive dress, then the minimum they can manufacture is 0. So we don't expect to have negative values for the number of dresses. And that is the idea for introducing the non-negativity. So once we formulated the model, once we formulated the problem, the question now wants us to solve it using simplex method. And it wants us to determine the number of standard and executive dresses. So there are many ways of solving linear programming problem. You can solve it using graphical method, but the graphical method has its own limitations because you must have two constraints. In this case, we can use graphical method, not two constraints, but I mean two variables x and y. In instances where we have more than two variables, graphical method becomes a problem. But in this case, if we are to solve this using graphical method, then it is possible. And we've already discussed graphical method before. So for now, I want us to talk about simplex method because most students, they always have difficulties understanding how simplex method works. The weaknesses of simultaneous equation, the weaknesses of graphical method are actually solved by simplex method. So for us to use simplex method, the first thing we need to do is that we need to develop a standardized model by introducing slack variables. And the idea of slack variables is that the slacks represents unused resources of the constraints. And in this case, the number of slack variables that we are going to introduce will depend with the number of constraints that we have. But the number of constraints excludes the non-negativity. So that in this case, because we only have the cutting department hours and the sewing department hours, we have two constraints. And because we have two constraints, we will introduce two slack variables. So that the first constraint will have the slack variable S1 and the second constraint will have the slack variable S2. But when we introduce the slack variables in our model, we'll change the inequality to equations. So that once we've introduced the equations or the slack variables into our models, we'll also include the slack variables in our objective function. So the slack variable will be in the objective function. At the same time, it will also be part of the constraints. But the only difference is that when you introduce the slack variables in the objective function, since the slack do not contribute to maximization objective, they are assigned coefficients of 0 in the objective function. So that if I want to introduce the slack variables and develop a standard model, then this is how it will look like. So this is a standard model. So that allow the maximum profit will be equal to 500x plus 800y. But because I have two slack variables to introduce, I'll say 0 is 1. And I'm assigning it coefficient of 0 is because we are saying that the slacks do not contribute to maximization. And this is just meant to adjust the constraints without affecting the objective function. That is why we assign the slack variables coefficients of 0. So that allow 0 is 1 in the objective function and 0 is 2. If I had 3 slack variables, I could have had 0s1, 0s2, 0s3. Now that I've introduced it in the objective function, I'll say subject to the first constraint I'll have is 10x plus 20y. But because this is the first constraint, I'll assign it the slack variable s1, and I change the inequality to equality and say is equal to 320. And the next one I'll say is 30x plus 40y plus s2 equals to 500 and 540. So now that I have the slack variables introduced, I can also still show the non-negativity and say that xy, s1, s2 should be greater than or equal to 0. So this is how you develop the standard. This is how you develop the standard model. Once you've developed the standard model, from this standard model now we develop the initial tableau. When we say the initial tableau or the initial table, we have to draw the first table for our simplex problem. And the good thing about the initial tableau is that we'll just take our variables and their coefficients as they are and make them part of our first tableau. So how do we draw the initial tableau? The initial tableau will have, we can call it the CJ row. The CJ row represents the unit contribution or the unit profit of our objective function, and it will have the variables of the objective function. And we have the CJ row, which is a summation of the product of the coefficients and their constraints. So that if I want to develop the initial tableau, this is how it will appear. I call this tableau 1. Then in my tableau 1, I'll introduce a row known as the CJ row. And this CJ row will have variables of the objective function together with their coefficient, so that if I have the variable x, the coefficient there is 500. If I have the variable y, the coefficient there is 800. And remember, x and y are our decision variables. Then we have s1 to represent the first slack, s2 to represent the second slack, and we know the coefficients are 0. Then we have the RHS. RHS represent the right-hand side values. So if you go back to our constraints, these are the right-hand side values of the constraint. The 320, the 540 are the right-hand side values. And because in our objective function we don't have the right-hand side values, then we don't expect to have anything there. That is how we have the CJ row. And in most cases, the CJ row will remain constant because the unit contribution of the decision variable is assumed to be known and constant. And we don't expect the CJ row to change as you move from one W to the next. So once I've introduced the CJ row, then now I introduce our two slack variables to represent our two constraints. Because I have constraint 1 and constraint 2, I'll introduce the slack variable, which is S1, and I'll also introduce the slack variable S2. So that when I start with S1, the coefficient of X in the first constraint is 10. The coefficient of Y is 20. And because this is S1, the coefficient there is 1. And because there is no S2 in the first constraint, I'll have it as 0. and we'll have the right hand side value of 320. We do the same for the second constraint. The coefficient of x is 30. The coefficient of y is 40. There is no S1 in the second constraint, we'll have it as 0. And the coefficient of S1 is 1. And this is 540. So we've assigned the coefficients of our constraints to each variable in the constraint. And once we've introduced the slack variables, in most cases, the initial tableau is always set at 0. And the reason why we set the initial tableau at 0 is because it is from tableau 1 that we are trying to assign resources. So that we have to start at the point of origin and assume that there is no resource that has been allocated. So that if the coefficient of S1 is 0, then to the left-hand side of our constraints, it will have a coefficient of 0. If the coefficient of S2 is 0, then to the left-hand side of our constraint, it will have a coefficient of 0. And if you assign these zeros, it will mean that at the point of W1, if you look at S1, the available resources, if you look at it through where we have this identity matrix, where we have the 1, it looks like an identity matrix, something of that sort. If I connect S1 with, we have 320, which means at this point, 320 resources are available, or 320 hours from the cutting department are available and has not been utilized. If you look at S2 and you connect it with 1, 540 hours are available from which department? We said from the sewing department and has not been utilized. And that is the whole idea. So the resources are available at full capacity, but you'll realize that as we move from W1 to W2, the right-hand side values will be changing, and that will now show the usage of resources until we arrive at a point of optimality. Okay. So once we've done this, we introduce another row known as the ZJ row. Introduce a row known as the ZJ row, which is a summation of the product of the constraints and their coefficients. So that if I want to get the first value of this ZJ row, then I'll take this is 10 times 0 plus 30 times 0, which is 0. 20 times 0 plus 40 times 0, which is 0. 1 times 0 plus 0 times 0, which is 0. 0 times 0 plus 1 times 0, which is 0. And 320 times 0 plus 540 times 0, which is 0. So you'll realize that at this point, because you've not yet started using the available resources, our ZJ values are actually zeros. And the ZJ actually represents where we have our profit. And this actually implies that where we have 0 on the right-hand side, it actually implies that at this point, the profit is 0. And at this point, the resources are available at full capacity. And that is why we are having all these zeros. So after introducing the ZJ row, we can introduce another row known as the CJ minus ZJ row. And this is the row that we use to test for optimality. So that if you want to know whether the solution is optimal for a maximization problem, then we check whether all the values of the CJ minus ZJ are less than or equal to 0. And because at this point the resources have not been utilized and the profit is 0, when you take your Cj minus Zj, which is in this case is 500 minus 0, is 500. 800 minus 0 is 800. 0 minus 0 is 0. 0 minus 0 is 0. And for this, we can ignore this. For the right-hand side value, we don't need because there is nothing here. So we can as well just ignore that. Or if you don't want to put x, because x may look like, let me just make it something that is not, it's less dramatic, and just put a dash so that it becomes easy. So this is actually how we develop our initial tableau, and we can, this is our tableau 1. So once we've drawn tableau 1, we check for optimality, and we said that for the solution to be optimal under maximization problem, the Cj minus Zj values should be less than or equal to 0. So definitely from tableau 1, you don't expect optimality because number 1, our profit is 0, and the resources are available at full capacity. So this implies that no resource has been allocated. So at this point, we cannot say the solution is optimal. So from our tableau 1, we can easily tell that the solution is not optimal. The solution is not optimal. And how do we know it is not optimal? Because the Cj minus Zj values are not meeting this criteria of less than or equal to 0. And you can see that we have the 500 and the 800, which are all positive values. So if the solution is not optimal, what do? We have to move from tableau 1 to tableau 2, but before we switch from tableau 1 to tableau 2, we have to look for a pivot column and a pivot row. The pivot column has the entering variable, and the pivot row will have the leaving variable. So if you're looking for a pivot column, we look at the Cj minus Zj values, and we can always pick the highest value of the Cj minus Zj values to identify our pivot column. And you can see that if I look at the Cj minus Zj, the highest value is 800. So that I want to reduce this 800 so that I am in a position to meet this objective of Cj minus Zj being less than or equal to 0. So because 800 is my highest value, then in this case my pivot column will be column Y. So that this will be the pivot column. So this will be our pivot column. This will be the pivot column. And you can see that when highlighting the pivot column, I'm only focusing on the constraints. I'm not including the Zj because this represents the final profit. So now that I've developed the pivot column, the next thing that we need to identify is the pivot row. Another thing about the pivot column which I want us to note is that because this pivot column has variable y is the entering variable. Y is the entering variable. When I say entering variable, This is the variable that we'll use to swap with a variable in the pivot row as we move to W2. So the next thing we identify is the pivot row. And the pivot, while talking about the pivot row, we only focus on our constraints because we have S1 and S2. There are only two constraints. That is why we have S1 and S2. Remember, if the question had several constraints, we could have had more than S1 and S2. So when looking for our pivot row, we are only focusing on our constraints so that it can either be S1 or S2. So how do you decide on the pivot row? So for you to develop the pivot row, then we have to use the ratio and identify the pivot row. You have to use the ratio to identify the pivot row. So let me clear this one because I want to calculate this ratio here. This one was just meant to explain that this is actually a profit, so we don't need this. So if I want to get the pivot row, then I'll develop a ratio, and this is how our ratio will be. I'll take the right-hand side values. I divide by the coefficient in the pivot row. So that in this case, this will be 320 divided by 20 and 540 divided by 40. So when I take 320 divided by 20, when we take 320 divided by 20, we get the ratio of 16. And when you take 540 divided by 40, you get 13.5. So after computing the ratios, then we pick the least value of all our ratios. So in this case, the least is 13.5. So if the least is 13.5, then it means that this will be the pivot, this will be the pivot, this will be the pivot row. So now that I have both the pivot row and the pivot column, this pivot row, I want us to take note of the variable of this pivot row. In this case, this variable is S2. This S2 will represent the leaving variable. The leaving variable to mean that when we switch from W1 to W2, where there is S2 after adjusting this pivot row, where there is S2 will replace it with Y, and where there is 0 will replace it with the coefficient of Y, but that is in W2. That is why we are saying the entering variable, this variable Y will enter where we have S2. So please note that as we switch from W1 to W2, we'll switch the variables from Y to S2. The reason for doing that now, because we've already started allocating resources, and it means that now units of Y, remember Y was the executive dress, units of the executive dress are now being produced. And you'll realize that as we switch from Y to S2, now we are utilizing that unutilized capacity of the resources. So we don't expect the resources available in terms of labor hours to remain the same. So as much as the labor hours reduces, the units produced also does what? Increases. And that is why we have to swap the decision variable with the coefficient of our slack variable. So now that we have both the pivot column and the pivot row, at the point of intersection where they meet is what is known is where we have the key element or the pivot element. So that in this case, at the joint where they meet, in this case, our pivot element is 40. And the basic rule of thumb is that the pivot element must always be 1. The pivot element must always be 1. And everything else representing the constraint must be 0. So that in this case where we have 40, we need to make this coefficient here to be 1. And within the same column representing the constraint, we have to make it to be 0. So that where there is 40, we have to make this 1. And where there is 20, we have to make it to be 0. So the idea of having zeros and ones is that it's just meant for easy operations, because whatever we are doing is the equivalent of sensitivity analysis, because in this case, it's like we are saying we are doing sensitivity analysis on our second constraint, which is S2. And if I take you back to some basics of sensitivity analysis so that you can try to get a relation, we always say that under sensitivity analysis or under shadow pricing, we always say that when carrying out sensitivity analysis on a particular variable, everything else remains constant other than the variable whose sensitivity we are measuring. So because my key row or my pivot row is S2, I'm focusing on utilizing resources on S2 and distributing it on the other on other constraint. But I want to focus on S2 while making the other variables constant. So for it to be easy for us to do that, then our key variable will assign it a coefficient of 1, and the other variable, which are not the key variable currently, will assign them coefficient of 0. So assigning them coefficient of 0 is equivalent to making those other variables, or in this case, those other constraints, constant. So that I want to make S1 constant by making sure that where there is 20, we have 0, and where there is 40, we have 1. And using a unit of 1 makes it easier to carry out sensitivity analysis so that a 1 unit change can actually be established. That is why we always make the pivot element to be 1. So there's nothing really special with 1, but it's just meant to make, when you measure change based on a 1 unit change, it becomes very easy to do the computation. So now that we've said that the pivot element must always be 1, and all the other elements in the column representing the constraint must be 0, then how do we make this 40 to be 1? So if you want to make this 40 to be 1, we can actually do some computation. Let's call this as working 1. And in our working 1, we can have our decision variables x and y. We can have our constraint not S1 and S2, and we can have the right-hand side values. As per our initial tableau, we know that this is 30, this is 40, this is 0, this is 1, and this is 540. And remember, this is our pivot row, this is our key row. But now the problem with our pivot row is that the pivot element is 40. And we want to make this pivot element to be 1. So if you want to make this pivot element to be 1, you can decide to multiply everything through by 1 over 40. So that when I say 1 over 40 times 40, it will definitely make that to be 1. But because all these elements are part of a set, remember we talked about sets, we cannot adjust only the 40. So everything else within that set we also have to multiply by 1/40. So that this will be 3/4. This will be 1 that we want. So this is our official pivot element, which now it's 1. 140, 1/40 times 0. This is 0. 1/40 times 1. This is 1/40. And 1/40 times 540. I think we already did that, but 540 divided by 40, we say it is 13.5. So this is now the official pivot row. The reason why I'm saying it is the official pivot row is because it is the pivot row whose pivot element is 1. So that when you are moving from W1 to W2, please note that you'll move the official pivot row whose pivot element is 1. And this official pivot row is the one that will take it to W, will move it to W2. So now that we've made the pivot element to be 1, remember what we said, we have to make the other constraint a constant by changing the element here to be 0. So if you want to make this element here to be 0, the easiest thing will be that someone else may say we multiply by 0, but you'll realize that if we say we multiply by 0, then it will make everything else to be 0. So it is not true that if I want to make this here, we multiply it by 0. Remember, I want to make this 0 without affecting our constraint. So if I want to make this 0 without affecting our constraint, then it means that we can use the official pivot row as a basis of making it to be 0. And that is why we don't always just go direct and change it 0. We want to adjust our official pivot row with the other constraint. And the idea of sensitivity analysis is that as much as you are changing a variable, it affects also the other one. So for us to make the other constraints 0, and in this case there is only one constraint, which is S1. But in another question that you may encounter, you may have had other constraints, maybe S1 and S3. So in that case, it means you'll make S1 0 and probably S3. But because it's only one, so please note that everything else representing the constraint could have been made to be 0. So for us to make this 20 to be 0, we've said that we use the official pivot row as the basis of making it to be 0. And the also possible reason for that is that we don't want to interfere with the structure. And the best way of not interfering with the structure is actually also using the official pivot column as a basis. So let's do our second adjustment. And let me call this working 2. And in my working 2, I'll have, let me call it old and new so that we know that there's a distinction. Let me have the oldest one. The oldest one as X, Y, S1, S2, and the right hand side values. So when I say oldest one, we'll just go to our initial tableau and we have 10, 21, 0, 3, 20. 10, 20, 1, 0, and 320. So this 20 is what we want to make to be. The 20 is what we want to make to be 0, not 1. Please note that we want to make that 20. We want to make that 20 to be 0. And we've said that for us to make this 20 to be 0, we don't just multiply by 0, but we use the official pivot row. Not just any pivot row, but the official pivot row. And how do you know the official pivot row? The one whose pivot element is 1. So that the official pivot row is 3/4, 1, 0, 1/40, and 13.5. So if this is the official pivot row, remember we are saying we are using the pivot element 1 as a basis of making this to be 0. So if we are using the pivot element 1 as a basis of making this to be 0, then it means we have to multiply this 1 by a certain value so that when we add or subtract, we end up with 0. So I know that the coefficient of y in S1 is 20 and this is 1. So if I want to end up with 0, then I can multiply everything here with negative 20. So that when I say negative 20 times 1, I end up with negative 20. So that 20 minus 20 will be 0. A very common problem that I also see students make is that when I say minus 20, I've already introduced the sign. So don't go ahead and say minus minus. The idea is not to minus. The idea is to add or subtract depending with what gives us 0. Because if this value here was minus 20, then it could have implied that I could have said plus 20. So once you've introduced the sign is final. So you will not say minus minus. But I cannot change only this single coefficient. So I have to multiply all the elements in the set with negative 20. So that this would be negative 20 times 3/4. That will be negative 60/4. Negative 60/4 is the same as saying negative 15. And then this is negative 20 because this is negative 20 times 1. Negative 20 times 0 is 0. Negative 20 times 1/40, this is negative a half. Negative 20 times 13.5. Negative 20 times 13.5. So that one we are saying 13.5 times 20. We get 270. So after doing that, now we can get the new S1. And this new S1 that we are talking about, this new S1 is what will move. We'll move this new S1 to W2. We'll move the new S1 to W2 so that now it will be 10 minus 15 is minus 5. Remember, I'm not saying minus minus. The sign that we've already introduced is final. And definitely here there's a negative. Let me just correct this is also a negative. The sign that we've introduced is final. Don't say minus minus. So this is 10 minus 15, which is negative 5. 20 minus 20, which is 0. And this is 1. And this is negative a half. 320 minus 270, this is 50. So this is now our new S1 that will go to W2. And because we don't have any other constraint to adjust, now we'll move to W2. And you can clearly see that now we've made this to be 0. And that was the goal. And we've made the pivot element to be 1. So once we've done that, bearing in mind what we said about the entering and the leaving variable, now we can draw W2. So let's go to W2. So when you go to W2, we said our Cj coefficients will remain the same. So it doesn't matter as we move, the Cj will remain the same because the unit contribution is still 800 for the first product, 500 for the first product, and 800 for the second product. So that the variable there is X and Y. Then we have 0 for S1 and 0 for S2 and the right hand side values. So the CJ row remains constant all the way through. So let's go back to our initial tableau. Remember in tableau 1, we add the S1. And the S1, the original S1, the coefficient here was 20, but now we've made this to be 0. And remember, this was not our pivot row. Our pivot row was S2. So when recording S1, we'll not take this S1, but we'll take the S1 that we've made its element to be 0. And that is why we say that this is the new S1 that we move to W2. So we'll have our S1, and the coefficient now will be -5, 0, 1, -0.5, and the right hand side value is 50. And you can see at this point that because this is still S1, the coefficient here will still be 0. But as we move to the next constraint, remember our constraint was S2, and S2 was representing the pivot row. And we said that because this is the pivot row, we will not have S2 as the variable. The variable S2 will leave because we've already started allocating resources. The variable S2 will leave and we'll replace it with the variable Y. That is why we said that you swap the coefficient of the pivot, not the coefficient, but the variable of the pivot column is swapped with the variable of the pivot row. So instead of saying S2, we'll now change the variable there to Y. Because why are we saying Y? Because we say that Y is the entering variable. So that we replace that with Y. And now because we have Y, the coefficient of Y here is 800. Then remember this was the pivot row, but in our initial tableau, the pivot row had a pivot element of 40, but we've already made this to be 1. So we have to take now the elements of the official pivot row, whose pivot element is 1. That is the one that we move to tableau 2. So we'll have 3/4, 1, 0, 1/40, and 13.5. So that our values now will be 3/4, and the other one we said is 1, 0, 1/40, and 13.5. 1, 0, 1/40, and 13.5. And you can clearly see now from here that we've made the pivot element 1, and everything else in the column representing the constraint is 0. We only have 1, 0 because we only had one constraint. And this shows that now we've already sorted column Y, the pivot column, together with its pivot row. So once you've done that, now we again develop the row known as the ZJ row. So that when we develop the ZJ row, then our ZJ row now will be 0 times -5 plus 800 times 3/4. So 800 times 3/4. So we'll say 800 times, we can say times 3/4. 800 times 3/4. Let me just confirm if that is okay. Because let me be certain. That is times 800. That is 600. So that's okay. That is 600. Then the next one we have is 0 times 0 plus 800 times 1. This is 800. 0 times 1 plus 800 times 0. This is definitely 0. 0 times negative a half is 0. 800 times 1/40. So that is 20. And then the last one we have is 0 times 50 plus 800 times 13.5. 800 times 13.5. So 800 times 13.5. That is 10,000. 10,800. 10,800. So now that we have our ZJ row, again we introduce the row that we test for optimality by taking the CJ minus ZJ. So that when you take the CJ minus ZJ, this is 500 minus 600. This is minus 100. 800 minus 800 is 0. 0 minus 0 is 0. And 0 minus 20 is minus 20. And this is our CJ minus ZJ row. Then we check whether it has met our condition. Remember, the condition for the solution to be optimal is that CJ minus ZJ must be less than or equal to 0. And you can clearly see that all the values of our CJ minus ZJ are less than or equal to 0. Then at this point, we'll say that the solution is optimal. So if the solution is optimal, then this implies that W2 is the final tableau. W2 is the final tableau. So after reaching optimality, how do you interpret this W2? How do you make sense of this W2? Remember what we said at the beginning, and if I take you back in the table 1, we said that if I take you back in table 1 in our initial tableau, I will say that at this point we said the profit was 0 and all the resources were fully available. The 320 was not utilized and the 540 was not utilized. But now you'll realize that as we switch from table 1 to table 2, you'll realize that now in table 2, the ZJ that represents the profit in the right hand side, this time round, our profit is 10,800. And this 13.5, remember the 800, this 800 is the unit profit. This is a profit per unit of Y. So if 800 is the profit per unit of Y, then it means that the 13.5, this is 13.5, these are units. Which means that for our decision variable Y, we need to produce and sell 13.5 units of y, but you'll realize that we don't have the other decision variable x. The other decision variable x has not been added to our basis in the constraint. So if you see that the other decision variable x is not in our constraint, the other variable remaining is S1. But you know S1 represents the slack. And remember what we said, the slack represents unutilized capacity. And S1 was representing the labor hours in the cutting department. So this means that if you interpret this from our right-hand side value, it means that 50 hours has not been utilized. 50 hours has not been utilized. That is what it implies. And only one decision variable y has been assigned. So which means that for the decision variable x, no units of decision of variable x has been produced and sold. So that the production of x is 0, but the production of y is 13.5. And you can see that we can confirm this position. If you want to know whether this is actually true, let's do the manual computation, because our final conclusion that we are making from this is that the maximum profit that the company can make is shillings 10,800, and they'll maximize this profit by producing 0 units of x. Why are we saying 0 units of x? That it has not been assigned to our constraint. The only decision variable, remember our decision variables are only x and y. We've assigned y to our constraint, and we are able to produce and sell 13.5 units of y. Because we've not assigned x, so 0 units of x will be produced, and 13.5 units of y will be produced. And this is what will maximize profit. And of our available resources, 50 labor hours of constraint S1 will not be utilized. But let's confirm that what we are saying is actually true. If you want to confirm this, let's go back to objective function and try and confirm this. If we go back to objective function, we said that maximum profit is given by 500x plus 800y. It's given by 500x plus 800y. 500x plus 800y. So if that is the case, we know that x is 0. So it is 500 times 0 plus 800 times 13.5, which you can clearly see it will give us the same profit of 10,800. But let's go to our constraint and see whether what we are saying is true, that the only constraint that should be unutilized. So the only constraint that should be unutilized is in S1, we are saying that it's days 50. So let's see whether that will be true. If we go to our constraint, our first constraint was 10x plus 2y plus S1 is equals to 320. That is 10x plus 2y, 10x plus 2y. Is it 2y or 20y? We are saying 10x plus 20y plus S1 is equals to 320. Let's see what happens. If we say that and we already have our values of x and y, then it will mean that we have 10 times 0 plus 20 times 13.5 plus S1 should be equal to 320. Let's see whether all these labor hours was fully utilized. So that will be 20 times 13.5, 20 times 13.5, 20, we have 200 and 270. So this implies that of the 320 hours available, 270 has been utilized, which means that S1 has not, will be, the amount not utilized will actually be 50 hours. And this is very consistent with what we have in our final tableau. And that is why the right-hand side values, we have 50 to represent that unutilized resource. But it doesn't mean that there is no optimality. Remember, this is where we are saying that the company is able to get the maximum profit from the available resources. So it doesn't necessarily mean that you have to exhaust what you have in order to maximize your profit. Because remember, the part of profit that we have is also the element of cost. Let's also try the same for the other variable. Not variable, but the second constraint. Our second constraint was 30x plus 40y plus S2 is equals to 540. So we'll say that this is 30x plus 40y plus S2 is equals to 540. So that this is 30 times 0 plus 40 times 13.5 plus S2 should be equal to 540. So that this will be 40 times 13.5. 40 times 13.5. And 40 times 13.5 would be 540. So that you can see that of the 540 available, the 540 has been utilized. So in that case, from this department, there is no labor hours that was available, that was left remaining. And what we are getting is consistent with our final tableau. So we can conclude that the maximum profit the company can make is 10,800 by producing 0 units of X. Remember, X was representing what? That is what we said. X now has been defined. We said let X be what? The number of standard dresses to be produced and sold. So which means that if this company wants to maximize profit, the number of standard dresses they need to produce and sell is 0. And the number of executive dresses they need to produce and sell is 13.5 units. The reason we say 13.5 is because there is the assumption of continuity. So we just say 13.5. And the maximum profit they can make is 10,800.